This lesson covers electrical safety and some of the designs that keep us safe. It's a topic that's really important for everyone to learn about, whether you're into physics or not, so let's get started. Let's start with the one you hold every day. Now, this is a UK plug, but the idea holds true in most places, even if the colours vary. That's right, the colours are important, and in most places it would be illegal to use the wrong one. So, before we go forward, can you say what the different parts of a plug are? See if you can put in labels for all of them. The one at the top, the one on its own, that's the earth wire. Then we have the neutral wire and the live wire opposite one another. And then our first three safety features. There's a fuse here, which I'll spend more time on in a minute. There's an outer casing that protects the wires from physical damage, which could lead to exposing a wire. And then there's a cable grip that helps if you accidentally or mindlessly or just plain wrongly try to pull the plug out by pulling the cable. Don't do that, ever. You risk pulling the wires out and electrocuting yourself. The live wire and the neutral wire have nothing to do with safety. The live wire drives electricity into your device, and the neutral wire completes the circuit. So let's have a think about how these things come together, and we're going to focus on trying to stop the electricity from hurting people. Here's an appliance. It's got an outer box, and the electricity is coming in through the live wire, doing its thing, then returning along the neutral wire. What happens if something goes wrong? TVs and things have holes in them to let hot air get out. What if you drop something in and it goes inside, like a paperclip or a staple, something metallic? It might cause a short circuit to the casing, which is not terrible by itself. When we talk about safety, we're not actually concerned with damaging appliances. We only care about you. The problem is, if you touch the appliance now, you'll get a very nasty electrical shock because you will complete the circuit, allowing the current to flow through you to earth. So, how does our plug help? Let's look at what happens if we attach the case to earth. Something has fallen in, or a mouse has eaten the cable, so we have a short circuit from the live wire to the case. This means the current can go through the case with low resistance, so there is a large current. This large current causes the thin wire in the fuse to melt. The circuit is now broken, so the current stops. This means it is now safe to touch the appliance. It won't work again until the fuse is changed, but safety first. Here we can see a close-up picture of a fuse. Notice how it's just a thin coiled wire. When a high current goes through, the wire melts and the circuit is cut. Fuses are bought with a maximum current rating, such as 3 amps or 13 amps. If your appliance needs a current of 5 amps to run, you would need the 13 amp fuse. So you use the fuse that is rated higher than the appliance. Otherwise, the fuse is going to break every time you switch on. So the most important safety feature is a way to cut the electricity if there is a problem. This is done by opening the circuit, either with a fuse, as we just saw, or a circuit breaker. This one works by using a bimetallic strip. If a large current runs through the circuit, the bimetallic strip will heat up due to resistance heating. It will then bend upwards. So the spring will pull the brass connector down and the circuit will cut. What will happen when the strip cools down again? What do you think? Will it go back to normal? Well, not quite, because the brass contact is still down. Someone needs to go and reset the circuit breaker after checking what caused the fault. A relay is not always thought of as a safety device, but that's one of its main functions. Later in the course we will learn about electromagnets in more detail, but at the moment we don't need to know how this works, just what it does. On the left we have a coil. When electricity runs through the coil, we get a magnetic field. The armature up there is simply a piece of magnetic iron on a pivot. When the current flows then, the armature gets pulled down here, which pivots the other side up there and to the right, like so. This pushes the switch contacts shut, which lets electricity flow through this other circuit. There's no electricity flowing from one circuit to the other. If the coil is turned off and the armature drops back, the springy switch contacts will open up again. So why is that a safety device? Take a moment to think about it. Notice, remember, the two circuits are separated. Well, what if the circuit on the right was at 240 volts or even higher, say 10,000 volts? That is quite dangerous for humans, and we should keep well away. I know I've had electric shocks just from turning the switch off for a Van de Graaff generator. Instead of going anywhere near that circuit, if we use a low voltage circuit on my side to control a relay, then I'm going to be much safer. These are also used to protect delicate equipment. Basically, the relay allows a low voltage circuit to switch a separate high voltage circuit on or off. Electrical safety is really important. We're using electronic components all day, every day, or so it seems, so we need to make sure we're using them correctly and we're using them safely. In this lesson we've looked at a number of different ways. It starts with the plug, and we've got the earth, we've got the fuse, we've got the cable grips as well. But then we could also instead use circuit breakers, and we've also thought about how we could have a design for a circuit breaker using a bimetallic strip, and how we can keep ourselves away from the dangerous electricity by using a relay. Now that's all well and good, but we also have to make sure we're making some sensible choices in our everyday lives. One of the things that I sometimes worry about, because I see it happening all the time, is the use of extension leads. You all know them. You plug them into the wall, you've got a long cable, and then you're able to plug other things in. Maybe you have 4 things being plugged in. But have you thought about if you're using them safely or not? Think about this problem. Now, if your extension lead rolls up like this, there could be a problem. Remember how current can heat up a wire? That happens in these too. What would happen if there was too much heat? Well, the plastic could melt because it gets too hot. There are 3 ways to try and fix this problem, but only 2 of them work. 1, unroll the extension lead fully. 2, buy a more expensive extension lead with a thicker wire. 3, buy a more expensive extension lead with thicker plastic. Which of those will help solve this problem? Okay, if you haven't got an answer, pause this and have a think about it. Now then, the air is cool, the wire is hot. So unrolling the extension lead will allow the surface area to increase and let it cool down more quickly. That's good. Getting a lead with thicker wire will reduce the resistance. Remember that resistance is proportional to 1 over the cross-sectional area. Less resistance means less resistive heating. That means less heat. That's good. Thicker plastic means the heat will be kept inside. and it will get hotter and hotter and then melt. And then it could end up looking like this. And then this. So always buy high quality electrical products, read the instructions and follow the instructions.